Okay, I'm going to get started. Today, I'm your host, Angela Wilkins. I work at Rice University. This is the Data Science Coast to Coast series. It's a seminar series hosted jointly by 7 academic institutes, academic data science institutes. 5 seminars will be in the spring that will feature faculty and postdocs. These seminars will be launching point for following up on research discussions and meeting with it, which will hopefully lead to collaborations. Here are the group of us all together. This is the itinerary for the semester. Today we're doing urban informatics. In April, we be looking at data equity and open science. The idea is we have 2 separate talks with a discussion at the end. Our first talk today will be Arya Ferrari. He will be talking about fair decision support systems and mobility challenges in the city of Detroit. He is a Michigan Data Science Fellowship at the University of Michigan. Looking forward to hearing his talk today. We also have Kate Starbird. She is an associate professor of human-centered design and engineering at the University of Washington, and she will be discussing revealing the big lie methodology innovation for the rapid response to online disinformation. You stop sharing so Arya can take over, and I will drop myself out. Thank you.
Yeah, thank you, Angela. All right, thank you so much for the introduction. Actually, I decided to change my title to be more representative of the talk that I'm going to give. So basically in this talk, I'm going to look at how we can quantify and mitigate different sources of bias in an AI decision support system. And I'm going to talk a little bit about the projects that we are doing with the city of Detroit. So basically, I'm going to start this presentation with discussing some of our ongoing projects with the city of Detroit. Then I'm going to use this project to motivate why we want to look at the trustworthiness and fairness of AI models, especially in decision support systems. And then I will discuss different sources of bias in a decision-making pipeline and illustrate a set of tools that our team are developing to quantify and mitigate those sources of bias. So in early 2020, Donald Kutra and myself co-founded Michigan Data Informed Cities for Everyone. This is a research collaboration, and the idea behind this research collaboration is to partnering with the cities and nonprofit and help them to develop and deploy data-driven solutions to some of the emerging challenges they have in their communities. This research collaboration started with the 3-year research agreement between us and the city of Detroit. So far, we have 3 ongoing projects with them. And on our team, we have 1 faculty member, 2 postdocs, and 10 students who are contributing to different aspects of these projects. So actually, I'm going to talk about one of these projects, which I'm currently leading within MDICE. In this project, the city partnered with us to develop a recommendation system to help them to address some of the questions they have in degrading infrastructure in the state of Michigan. Specifically, we are looking at the road conditions in the city of Detroit. Detroit is actually one of the worst cities nationwide in terms of its road condition. Actually, if we look at the numbers, the percentage of roads which are in poor condition is around 58% in the city of Detroit, compared to the city of Ann Arbor, which is 20%. And the idea is that we want to bring this number to 20% to be more consistent with the nationwide numbers. All right, but there are a lot of challenges within the city of Detroit, and there are a lot of bottlenecks. The city does not have enough resources to fix all the degrading roads and the poor infrastructure they have in the city. And there are a lot of bottlenecks, and we want to identify different bottlenecks and try to solve them. One of these bottlenecks is the road assessment task. Typically, they have to hire someone. This person have to go to the place, perform some measurement, collect some data, send back this data to the city. They are going to aggregate this data and make some decision based on this data. And now we are wanted to automate this process. To initiate this project, the city collected around 3 million images across the city. And then we are going to take those images, identify cracks and potholes across the city, measure some of the properties of these cracks and potholes, and see how they are distributed across the city. And because every 6 months they get a new set of images, now we can look and see how these cracks and potholes degrade over time. Now we can build a statistical model to quantify the condition of each road segments. Then we are going to send this information to a recommendation system that we are developing. This recommendation system is going to combine this information with population data, occupancy data, traffic volume data. We are going to look at the bus ridership data. We are going to look at some of the public assets that are owned by the city, construct a utility function, perform a cost-benefit analysis, and then we are going to maximize the benefit for the residents. Basically, we are going to identify which road segments, if they get fixed, they provide the maximum benefit to the residents. And then we are going to propose them to the decision makers. And to help the decision maker to better understand what is happening underneath of this pipeline, we are going to implement a UI system for them so they can visualize the output of this recommendation system. And hopefully it is going to help them to develop budget planning and make their final decision. And it is going to save a lot of time and money for the decision makers. But if we look at the literature, there are a lot of discussions within and outside of the community about the implications of these AI systems that we are developing on our society. And we have seen news headlines and examples on how algorithms has negatively impacted the underrepresented population. So we have to be very careful about how we are designing these algorithms and when we are going to deploy them into the real world setting. Basically, in the start of this project, we started to think a lot about the potential fairness implications of this AI system that we are developing and how it might impact the life of the residents. For instance, here I took some of the historical data that the city already has. Here I stratified the census block in terms of the poverty rate and the household income, and looked at the distribution of the average road quality. And one thing that is obvious is the fact that the poverty rate and the household income of your neighborhood determines what type of road condition you have in your neighborhood. And this is exactly the type of situation that we want to avoid. And we don't want to exacerbate these biases that we have in the city. Actually, we want to see that if our AI system is going to be deployed in the city, it is going to reduce these biases that we are seeing in the historical data. So now the question is that how we can quantify the fairness in a historical data or in a decision-making system. So basically, we are going to use this idea. We are saying that we can split our data sets, which are the road segments in terms of their condition. We are going to, it is a binary variable, whether they are in a good condition or they are in a poor condition. And we are going to look at the joint distribution of our socioeconomic features. All right, so let me set up the problem first. Let's imagine that we have a system U that is collection of n items. So basically in this problem, all road segments in the city make our system. And then each item at time t is described with two different quantities. And each item corresponds to a road segments in our data set. X is a d-dimensional feature vector based on which we want to quantify the fairness of this system. And S defines the status of item I, which is basically the condition of the road. It is a binary variable, whether they are 1 or 0, whether they are good or bad. And then we are going to define what it implies to be a fair state. A system is going to be a collective fair state if the socioeconomic features are independent of the state of our items. Then we are going to say that the system is in a fair state, or in another word, your socioeconomic feature is not going to determine what type of road conditions you have in your neighborhood. And then we are going to use this idea to quantify how much unfairness we have in a given data set. So basically, we are going to quantify the unfairness based on the distance between these two distributions. If the distance between these two distributions is exactly equal to 0, then we are in a fair state. Otherwise, we are in an unfair state. All right, now let's look at two different decision algorithms. One of them is a utility-based algorithm that only uses the utility function to identify which road segments we want to fix in the next batch of the maintenance cycle. And as you see, and it is showing how the unfairness progresses over time. So as you see here, it is not going to reduce the unfairness in the data. And it is not going to exacerbate it as well. But now we decided to incorporate some fairness into our cost function. And here it is showing that the unfairness is reduces over time. And actually after half a decade, we can reach into a state of fair. But always there is a trade-off between system level utility and fairness. And we have to be very careful. So if we are able to tolerate a little bit of inefficiency in our recommendation system, then we are able to achieve into a fair state. All right, so far I talked a lot about how we can make a decision and how we can quantify the fairness at the system level. But there are a lot of different tasks that we have to do before making the final decision. And now I wanted to ask a different question, how we can quantify whether an AI system that we are implementing into this decision support system is trustworthy or not. It is a completely different question that we are asking. So first we have to understand what are the potential sources of bias in an AI system, and then how we can mitigate, how we can identify them and how we can mitigate them. First, we have to identify a task or ask a question and construct some objective functions. These objective functions might be biased by construction. So we have to be very careful about how we are constructing those objective functions. Then we have to collect some data. Data are not always clean. Data can be noisy. The noise can be correlated with the protected features or sampled in a biased way. We can have missing value. This missingness can be correlated with the properties of the system that we are trying to model. But a central part of any decision support system are the models that we are deploying into them. Essentially, these models provide the information for the decision maker, and the decision makers are going to use those information to make their final decision. And it is the job of us as a modeler to make sure that the information that is passed by these models to the next layer of a decision-making pipeline is trustworthy. So basically, we want to address whether these models are passing trustworthy information to the decision maker or not. And then it is going to be the job of the decision maker how they want to use those information to make a fair decision. So basically, trustworthiness is a necessary condition for algorithmic fairness, but it is not going to be sufficient condition. All right, so let me talk about how we can quantify trustworthiness in a predictive model and what exactly I mean mathematically by trustworthiness. So I'm going to talk about trustworthiness in the context of probabilistic classifier, and I'm going to start with an example. Let's imagine that we have a predictive model that is going to predict the probability of developing cancer for a set of patients if they are given a treatment T. Now let's imagine that this probabilistic classifier is going to predict that for a subset of patients with 50% chance they are going to develop cancer. If this information is trustworthy, then for that subset of patients, eventually 50% of them have to develop cancer. If this number is 60 or 40%, that implies that this information is not trustworthy. So basically, I'm going to use trustworthy and calibration interchangeably in this talk. All right, now let's imagine that this subset of patients consists of 10% from a minority group A and 90% from a majority group B. Then we are going to run an observational study to find the frequency of developing cancer and evaluate the performance of this model. And we find that actually 95% of our patients in group A have developed cancer, as opposed to 45% in group B. If we do the math, actually we see that on average over our population, 50% of our patients have developed cancer, which implies that on average over the entire population, this information is trustworthy and it matches the frequency of our observation. But if we are concerned about each individual subgroup in our data, then this model is not trustworthy anymore because the prediction of this model does not match the frequency of our observation for each individual subgroup in our data sets. And the impact of this type of miscalibration or group-wise untrustworthiness is more damaging on the underrepresented population because the distance of prediction of this model for the underrepresented population is much larger than the majority population. And essentially in this clinical setting, we don't want to distribute our resources among our patients completely equally. We want to distribute the resources based on the need of each individual patient. So we have to make the decision makers want to have trustworthy information respect to each individual subgroup that we have in our data. So essentially in this setting, we want to have trustworthy information with respect to every subgroup we have in our data sets. All right, so now let's mathematically define what we mean by the trustworthiness. Let's imagine that we have a model F. Model F would be group-wise calibrated or trustworthy if and only if the prediction of this model matches the frequency of future observations for every subset of our population. Another thing which is very important about this definition is the fact that input of your classifier doesn't need to be identical to the feature set on which we want to test the trustworthiness of this model. So let's imagine that we want to predict the likelihood of developing cancer in our patients. The input of this classifier is age, genomic expression, and gender of our patients. And then a doctor comes and say that, okay, I want to make some decision about my patients, but I want to make sure that this information is trustworthy respect to age, gender, race, and income level of my patients simultaneously. So there can be an overlap between X and Z, but they don't need to be identical. It really depends on the question that they are asking, depend on the decision makers and the auditors, and what type of test they want to perform, and how they are going to define their groups. All right, so our solution is Kite. Kite is an open source solution for trustworthiness quantification. Essentially, it is going to perform hypothesis testing. It takes a model and prediction of the model, and we are assuming that we have some observational study, or we have a test sample for which we know the label of our data set, and then it is going to perform hypothesis testing, say whether our model is group-wise calibrated or trustworthy or not. And if it is not trustworthy, then it is going to perform calibration, estimate the group-wise biases, correct for those group-wise biases, and then give us a new model that is properly calibrated or trustworthy. To do this process, we introduce a new test statistic. I'm not going to dive into the theoretical properties of this test statistic, but essentially it is going to compute the rate of error, take the features and the model prediction and take them into a kernel space and compute the value of this test statistic. And we have shown that if this test statistic is exactly equal to 0, then our model is group-wise calibrated. So let's see how it works in a simulated setting. Then I'm going to show you how it is going to work in a real-world applications. So here I have 3 different classifiers. The first classifier is a calibrated classifier, or in another word, it is going to give us group-wise calibrated information. But the other 2 models are miscalibrated models. Then I'm going to pass all of these models to my hypothesis testing framework, and it is going to give me the value of the test statistic and p-value. P-value essentially quantifies with significance we can reject the null hypothesis. And in this case, the null hypothesis is that whether a model is trustworthy or not. So here we are showing that p-value for the blue model is pretty large, so we cannot reject the null hypothesis. So the blue model, as expected, is trustworthy or group-wise calibrated. But for the other 2 models, we can reject the null hypothesis, and we can say that they are group-wise miscalibrated. And the actual value of our test statistic can quantify how much untrustworthiness we have in our data, in our model. So essentially here, the orange model is less untrustworthy compared to the green model. And it allows us to perform all sorts of model comparison to see which one of the given models are less untrustworthy. And then we are going to pass all of these models to our calibrator. Our calibrator is going to estimate the group-wise biases, correct for those group-wise biases, and then we are going to perform hypothesis testing again. Here, after calibration, the value of our test statistic is pretty close to 0, and the p-value is pretty large, which implies that not all of these 3 models after calibration became trustworthy. All right, so now let me show you how it is working in a real world application. So here I took the Compass recidivism data sets. Compass, as you might know, is a data set that is used to predict recidivism. It asks whether a defendant is going to reoffend or not. So it is a binary prediction, and we are going to compute the risk score. And then we are going to ask whether those risk scores are calibrated or trustworthy with respect to age, race, and gender simultaneously. So here I trained a random forest algorithm, performed hypothesis testing. So here I don't know why this the picture is missing, but here it is showing the value of the test statistic and the p-value, and showing that the p-value is very much consistent with 0, and the value of test statistic is much larger than 0. So we can reject the null hypothesis, and this model is not trustworthy with respect to all of these 4 features simultaneously. So we cannot use this prediction of this model to make some decision about these people. All right, now we are going to pass this model to our calibrator, and our calibrator is going to estimate the group-wise biases. Here in the bottom, I am showing the group-wise biases for the defendant in our sample. And it is showing that these biases are a nonlinear function of gender, race, and age. So even if we are looking at one population, for example, non-African American, the value of this bias changes from whether they are male or female and at what age they are. So we have to be very careful about how we are designing our experiment, what type of questions we are asking, and what type of, how we want to define our groups in our data set. All right, so I hope that I gave you a flavor of what we are doing within MDICE. Just to remind you, the goal of MDICE are developing theoretical models and implement auditing tools to quantify and mitigate biases in an AI decision support system at all levels, at the data level, modeling level, and prediction level. And we are hoping to bring fair and trustworthy AI research to the forefront of decision-making process by working with the real stakeholders in the city of Detroit. And we are hoping to hear from you and learn more about how these tools or similar tools might be helpful in your research or in your applications. I'm going to turn it over to Kate, and happy to take any question after her talk. Thank you so much for your attention.
Thank you for that. That was really wonderful. I think just such an important topic about algorithmic bias, and I apologize to folks that this might be a little bit of a shift in both domain and methodology here as I get started with my talk. I am hoping you all can see. I'm getting weird feedback here. So I'm going to talk about the big lie, online disinformation around the 2020 election in the United States, and also talk about a collaboration, a data science kind of collaboration that we've been doing to do rapid response to disinformation in that context, and now in other contexts as well. I want to start here with a now familiar, but once horrifying, and probably should be still horrifying, photo of what I call hashtag patriots wandering the US Capitol building on January 6th. This was what we might talk about as an internet-enabled insurrection attempt at the United States Capitol, with the symbols and memes of internet culture come alive. And if we want to think about a possible explanation of what might have motivated that insurrection attempt, we need look no further than the Twitter account of the US president that day, where he repeats the false claim that his sacred landslide victory had been stolen from him and his followers, and where he refers to the insurrectionists as patriots. So in this context, I want to look back a little bit at election 2020 and talk about, how this was kind of a perfect storm for misinformation, and misinformation here. I'll talk a little bit about disinformation next. A perfect storm for misinformation with unprecedented and dynamic impacts from COVID-19, changes that were happening to the election infrastructure to accommodate that, uncertainty due to delays counting mail-in votes, and some of those delays were purposefully embedded in the system in order to amplify that uncertainty, and a heavily politicized and polarized information space. At the same time, there was also a disinformation campaign. This one was pushed by the US president and his supporters to try to sow distrust in the process and in the results, in part to insulate themselves from defeat, in part to push for future voter suppression measures that they seem to believe will help them obtain and maintain political power. Bankler et al. Actually wrote a little bit, published a report prior to the election, a few months prior, to talk about this as a disinformation campaign. And we agree with that framing, that this was a disinformation campaign. Before we get too far, I want to unpack these two terms, misinformation, disinformation. They're really important to understanding what's happening, especially in the political context, and to think about how we should respond to different kinds of false information. So misinformation is information that's false, but not necessarily intentionally false. Whereas disinformation is false or misleading information that's purposefully seeded and/or spread for a specific objective, whether that be financial, political, reputational, or otherwise. Some interesting things about disinformation is it's often built around a true or plausible core, where there's something true in the middle, but then it's layered with distortions and exaggerations, intending to shape how others perceive reality. Through this view, disinformation can sometimes be resistant to simple fact-checking, especially on a single piece of content. And it can't always be reduced to false information. It often functions not as a single piece of content, but as a campaign, as an assemblage of different information actions that are kind of put together in order to create these false realities. One of the sort of theories of disinformation, of things that we've begun to think is true as we see it kind of operating across different contexts, is that pervasive disinformation especially erodes the foundations of democratic societies, because it undermines our trust in information, in democratic governance, and in each other, and it kind of destabilizes the common ground that we need to stand upon to govern ourselves. So it's a threat in particular to democracy. When we look back a few years in the US context to disinformation 2016, there was this documented campaign. It was foreign, you know, the focus had been on the Russian disinformation efforts. There were other things going on as well, but the story of 2016 was a foreign campaign where a bunch of inauthentic actors were coordinating to spread disinformation in an attempt to interfere with the US election. This is very different in 2020, where what we largely saw was a domestic campaign coming from inside the United States. There were some foreign activities, but they weren't playing a large role. It wasn't inauthentic accounts, it's actually authentic or blue check or verified accounts, along with other more anonymous members of the connected crowd. And it wasn't entirely coordinated. In fact, in places it was very organic, bottom up, as well as top down. And I'm going to talk a little bit about some of those dynamics here. And I want to talk about this in the context of a project that my team at the University of Washington was participating in with others. We were actually collaborating in a multi-stakeholder collaboration for rapid response to online disinformation. And we're thinking about this as something that we could actually organize in the future and begin to maybe put out frameworks for others to kind of participate in these kinds of things as well. So I'm going to talk about this. It was the collaboration we participated in was the Election Integrity Partnership. It was a collaboration between the Stanford Internet Observatory, the DFR Lab, Graphica, and our team at the Center for an Informed Public at the University of Washington. We were participating in rapid response, real-time data analysis between the middle of August and through December 2020. We had to stop when the school quarter stopped, but actually we could have gone all the way into January, clearly. We had over 100 researchers, and we also had partners in government, tech platforms, and civil society. What we were trying to do is identify disinformation, rapidly track it, see where it was coming from, and be able to give a picture of who's spreading this, and possibly notify platforms of what was happening in hopes that they could take action, and occasionally they did. We were using a sort of open source analysis techniques, collecting mostly public data, almost exclusively public data, and using visualization tools, network analysis, and lightweight natural language processing tools in order to do some of this work. The goal of this work was to rapidly identify and address misleading information, particularly about election procedures, voter suppression and intimidation, and fraud. Eventually, our most prominent focus became on the efforts to delegitimize the election through false claims of voter fraud, which were part of this sort of long-term disinformation campaign. I want to point out that we have a final report we put out on this. It's like 400 pages long. It's very long, and I'm going to just highlight a couple of pieces here, but certainly, if you're interested in this, I can point you to that sort of final report. So to give some hints of kind of what was happening along the way here, I'm going to take you into a couple of the different places. So to think about this campaign, we have to remember that we have to kind of think about this. The claims of voter fraud didn't start with the election. They actually began to take shape long before the election. This tweet from former President Trump was sent in June, and it claimed that the election would be rigged against him. And this is something that kind of set the stage for many people who were followers of Donald Trump to think that this was something that might be happening, right? So they believed this. And over the course of the fall, we saw numerous incidents, we calling them incidents or events or cascades of false or misleading information, particularly about mail-in ballots, mostly prior to the election. Some were generally sowing distrust in mail-in voting. Others were explicitly claiming voter fraud. So here's an example from September of a photograph of a bunch of ballots that were in a trash area where they were being discarded, or they'd been discarded. And the claim was that this was somehow related to the election 2020, and that it was an example of how we couldn't trust the process. And of course, at the end, the person who's a right-wing media personality says, big if true. Well, it wasn't true. The ballots were actually from 2018. They were being recycled. But this fed into the narrative that the election was rigged or was going to be rigged. And eventually went viral. It was tweeted or retweeted more than 25,000 times. Our team tuned into it about maybe 15, 16 hours after it started to take off. We actually did notify the platforms. The platforms did take this particular tweet down. But the misinformation about this began to spread. And even once it was taken down, it just reaffirmed this idea that the mail-in voting couldn't be trusted, even though it was based on evidence that had nothing to do with the 2020 election. When we look at how it propagated, so we would graph a lot of these events to see how things were spreading in the online spaces. And this is one of the visualization techniques we use to kind of look not just how much volume something is gaining, but when does that volume shift and how do individual accounts play a role? So in this visualization, it's a cumulative volume of a particular narrative, not just one tweet, but of a particular narrative. And each, so volume is on the y-axis, time is on the x-axis, but then we plot individual tweets along the way that sized by the number of followers they have. So we can see the large following accounts and the role that they play in changing the trajectory of information. We also can see the difference between quote tweets, which are in red here in the diamonds, original tweets, which are green, and blue tweets, which are just retweets, and kind of see the different interplay of what's happening there. To get a peek at the propagation of this particular narrative, Elijah Schaefer posts it. We pick up one of his tweets here early on. It's kind of the first in this cascade, or it's the first major tweet in this cascade, but it begins to kind of gain steam and then eventually take off by being repeatedly retweeted, remixed, and reframed by other influential social media accounts and right-wing media outlets. Eventually it reaches the account of President Trump's son, and then it continues to spike from there. Although it's already begun to kind of reach saturation at that point. So this kind of trajectory is not uncommon. In fact, we saw very similar things happen over and over again, where networks of politically motivated information activists, social media influencers, and hyper-partisan media outlets were repeatedly picking up evidence of voting concerns, framing that evidence in misleading ways, and strategically amplifying that content to support meta-narratives that undermine trust in the election. So that campaign continued into the election and beyond, and went on for some time. I actually am going to skip these next few slides, but we actually, before the election, we put out a bunch of predictions about the kinds of narratives that we would see and how they were going to develop. We got some things wrong, but much of what we saw, we kind of could already see it happening before the election. We could tell that this narrative was beginning these ideas were converging. And we could see that people were being encouraged to gather evidence on election day from their voting experiences. And then they were going to assemble that evidence to fit false narratives of voter fraud. And then we had this kind of idea from seeing past elections that they would use bad statistics and premature declarations of victory to sow doubt and question shifts in vote share that were expected to happen based on the election. We also predicted it, and we saw legal complaints that in affidavits that were used to reinforce and give weight to these false claims as they began to spread. And certainly afterwards, many of the narratives that we expected, including others, began to develop into particular kinds of conspiracy theories around, ballots being moved around in nefarious ways, about dead people voting, claims that voting machines and software systems were switching votes, and plenty of statistics being tortured to claim that there was evidence of massive voter fraud. So a lot of different things happening in that space. When we look through across all of the data we collected, so we had 120 researchers collecting, we would work shifts, 4-hour shifts at a time, with different configurations of teams. And we identified nearly 1,000 different incidents of mis or disinformation about the 2020 election procedures, not just about the politics, but about the procedures and mostly claims of false claims of voter fraud. We look a little bit deeper. We did see some disinformation on the political left, particularly around before the election, around claims that the United States Postal Service was intentionally slowing the mail-in ballot process in order to sway the election towards Donald Trump. But those kinds of narratives were really dwarfed by what we saw on the right, on the political right, especially among pro-Trump social media accounts and hyper-partisan media. And I want to take you in detail through one particular narrative that's kind of really demonstrative of some of the dynamics that we saw of how these false and misleading narratives would take shape, including from people who actually believed them. So this one was about something that the people propagating it called Sharpiegate. And it started with this observation that people had, that their Sharpie pens that they were given to fill out their in-person votes were bleeding through the ballots. Well, it turned out the ballots had actually been designed to be used by Sharpie pens. They were designed so that the machine would read them and not register the bleed in on the other side. So they were designed in a way that the backside and front side didn't line up. So in any case, it wasn't an actual problem, but people perceived it as a problem. And in fact, the Maricopa County Elections Department in Arizona, where this became an issue, they put out many corrections to say it's fine, everything's fine, this is how it was designed. But people began to think that this might be part of the voter fraud that they had heard about. And so early on, we could see people posting content that shared sort of concern that their ballots might not be counted. And then that concern began to be suspicion that it was intentional and that possibly this might change the course of the election. And later on, it began to solidify in very specific accusations, in particular in Arizona, that specifically Trump voters had been disenfranchised by being forced to use Sharpie pens. Now, these were not true, but they were very compelling for the people that were sort of participating in these narratives. If we look at sort of a graph of how these narratives propagated over time, and kind of look at where it begins to take off. So early, the first, on election day, there was a few little tweets of people saying, oh, my ballot, my Sharpie's bleeding through, I don't know what's going on. But then it really begins to just take off. And that happens right when the state of Arizona is called for candidate Biden. And it was unexpected. And people in Arizona, the Republicans are looking for a reason why and how to claim voter fraud. And they were like, oh, it must be the Sharpie pens. And so this begins to take off because it's politically expedient at the time, right on late on election night and into the next day. And it was powered and largely propagated by conservative activists, influencers, and Donald Trump's 2 adult sons, who actually send this narrative into the stratosphere. And then it begins to spread very widely for some time and become part of the voter fraud myth that we all have heard now. So I want to talk about here how disinformation is participatory. President Trump and his campaign didn't just prime his audience to be receptive to false narratives of voter fraud. They inspired the audience to produce those narratives themselves and then echoed those false claims back to them. So it was this two-way dynamic. We can actually know these people, a lot of them, they sincerely believe they've been cheated. Here's a person that went online after she saw her ballot bleed through, went online to check and found that her ballot had been canceled. So very angry, is tweeting about this. Many people start to tweet about this, except if you look really closely, her ballot hadn't been canceled. Her mail-in ballot had been canceled when she voted in person. And she's actually misinterpreting this information within the frame of voter fraud and sharing it. So I would argue that, you know, this is a very compelling way to participate in a false narrative in a way that becomes almost uncorrectable, because the people that were spreading it actually very much believed it, in some cases created the narratives themselves. Where the elites have set the agenda, they've seeded the narratives, but the audience is sort of, it's crowdsourcing to find the best narrative, the most fit narrative or conspiracy theory that's going to spread widely and help reinforce these higher level narratives that have been set from the top down. The last thing I want to talk about here is how the networks are wired for disinformation. We've talked about, oh, it's hard to moderate content, you know, from the platforms, it's hard to track everything. But when we really look at what's happening, there are a small number of accounts that have an outsized impact on this campaign and how it spread. So we created, we went through an analysis. We had over 1,000 different incidents. We kind of condensed them a little bit to slightly fewer, about 600. And we looked at the accounts that were most active in spreading the highest number of different incidents. And in this case, we found accounts that were retweeted more than 1,000 times across different misinformation, disinformation incidents. And we had a network graph to kind of place them on the right versus the left. We used a composite retweet network graph that condenses the network to influencers by making edges cases where two accounts have been retweeted many times by many other accounts. So a little bit hard to explain in time here, but we have this graphing technique to kind of collapse the network to just the influencers. But if we look at this table of all the influencers that were most active, spreading, you know, 10s and sometimes 20 different disinformation narratives, they were all in pro-Trump influencer accounts in that network. If we look a little bit closer, Donald Trump and his 2 adult sons are among the top 20 perpetrators of mis and disinformation about the election. There are accounts of hyper-partisan news outlets, conservative activists, including Turning Point USA and Judicial Watch, other GOP affiliated accounts, and then the rest are other right-wing accounts with large followings, and also in yellow, QAnon accounts. So the point here is that it's not, there's a huge problem in terms of how these things spread, but we can actually identify a small number of influencers who were, you know, largely responsible for a lot of the mis and disinformation that we saw that ends up leading to January 6th and this sort of real world violent action that was motivated by these grievance-based false narratives. Interestingly, afterwards, we see this domino effect occurring through the online platforms as they begin to suspend accounts that had been prominent in spreading those false narratives. These are three of the four top accounts from our top 20 list that have been suspended. Other accounts from that list that were shadow banned, but many others are still active and still able to share information as well as misinformation. Here's a peek at what some of those suspensions did to the network that we had. So we were using this network, as I said, to track, you know, how different narratives spread in the left versus the right. The blue here is the left. The red is sort of mainstream pro-Trump accounts, and the yellow was a group of activists, more sort of QAnon accounts. And the suspensions, we've highlighted, those accounts here are in black, and you can see how the suspensions took out a huge section of the sort of QAnon and pro-Trump activist accounts in the network. So we are seeing these platforms begin to take action. Several have put in place civic integrity policies and policies about COVID-related misinformation as well. Twitter's actually introduced a repeat offenders policy in recent months, maybe the last 6 weeks or so, where they have a 5 strikes policy where if an account, you know, if the account ends up in our list, if they've spread, you know, false information 5 or more times, then they begin to take action, and increasingly strong action, including suspensions as they go. There's a long way to go, I think, with platform policy. It's certainly a huge need for clarity and transparency in the policies, and it's a lot of responsibility, and I would argue probably too much responsibility for individual platforms because the stakes are so high for society, as we've seen in these past events. And the last thing I want to talk about a little bit is the future of these kind of collaborations that we were doing, the kind of work we did to sort of document things in near real time, to both report on it and highlight it. We wrote blogs and got things out through journalism as things were happening. And then also, you know, tag things for platforms and others as we were going. Really interesting ethical questions, methodological questions for those kind of collaborations going forward. Certainly, we see a value to that, but there's a lot of hurdles that we need to get over to figure out how to make those run smoothly. So it's something we're really interested in working on in the future, and think is something both to research about these, but also do research through these. And we've also created what we think is a really interesting data set, because we had people annotating and trying to capture these very sometimes ephemeral informational events in the moment. So really excited about that, really happy to talk about that. I just want to give a shout out to all of our collaborators and students and postdocs. And this is just on the UW side, but again, there's hundreds of people involved in that project. And yeah, and thank you all for your time.
Thank you for a great talk. I had a question about the network. By the way, Aria, if you could pop up, this would be a good time. You had to label, here's the left, here's the right, here's pro-trope, here's QAnon. How did you make that decision? Because that seems very challenging when we talk about data bias. And
absolutely. I mean, the network structure comes from the way we're calculating things. And then what we do is we run a couple of different things. One is content analysis. We just go look at the accounts, we read the content. But in this, what we'll also do is grab the top hashtags that are shared either in the profile or in the tweets from those accounts. We'll also look at the domains that they're sharing in high frequency, and we use those kind of together to make these different, to make these kind of different determinations. Sometimes we're still really kind of unclear about the difference between the red and the yellow. We know that they come out structurally different. The content is often very similar. And so there's something behavioral and something about the networks that really separates those. The fact that when Twitter did their suspensions, they all went on one side and not as much on the other side, although Donald Trump is this big red account right there in the middle, in between the yellow and orange. And so his account and some around those were suspended. But there was some, so some of it is, yeah, we can get from the content signals, but some of it, clearly, some of what we're seeing in the network is also behavioral, because we think that Twitter used behavioral, something about their behavior in order to make those suspensions, although we don't, unfortunately, we don't know exactly what criteria they used. And I think that's part of the transparency thing that I think would be really important for us as researchers and society to better understand how these policies are being acted upon.
Yeah, I mean, from what I get out of what you're saying is that there might be something underlying in the signature of the network that actually caused them to make that choice. And so it'd be helpful because you might end up with something circular in there.
Yeah.
In the structure of the network, I noticed that there are some points where the red and yellow connected to the left. But I mean, I'm off the top of your head, I mean, you may not know, but what was going on there?
So in the central part, what's connecting the red and the blue is actually media outlets like The Hill that are highly cited and so highly retweeted by people both on the left and the right, because again, each edge isn't just one single retweet. It means several users retweeted both accounts multiple times. So these are, really kind of a stronger pattern before it shows up in our graph of retweets. So The Hill and some other kind of middle of the road media that.
Interesting.
And then there's some other really, I won't name names because I know it'll get me in trouble, but there's some really interesting ones between, like, one area of that is sort of much more in the light blue. There's also a dark blue section that is more of the sort of Bernie or stronger, like socialism kinds of accounts. So a little further left. And there's a place where they line up and start to connect with the right. And the accounts are exactly who you would predict who would be in between those. So there are, they're the influential accounts that that are prominent both in sort of pro-Trump networks and far left networks. So there's some really interesting dynamics there as well.
Yeah, because one of the things is like you might speculate that those points are good ways for us to increase conversation between the left and the right, because, well, maybe that would help.
Yeah, I mean, it does. They do highlight where there's an opportunity to reach both sides. Although I wouldn't say the Hill would be representative of the kind of content we'd want to be promoting to bring people back together to a shared reality.
We had a question come in, and Aria, I haven't forgotten you. I have a ton of questions for you, and if you want to ask Kate some questions, go for it. You too. I do have another question came in for Kate, and I want to make sure I get to it. While the focus of your work here is around the 2020 U.S. presidential election, do you think it would be possible to monitor the platforms for misinformation at large and get an estimation of how much misinformation is out there?
I think that's a huge task. I don't even pretend to make quantifications of how much misinformation is here, whether it's growing, whether it's shrinking. I think there are many who think that in the last year it's really grown. It would be really fascinating to see that. Our techniques, our methods wouldn't get us that. We're too reliant on having to manually identify different especially disinformation, because it's subtle. It's usually about the framing, and it's, you know, it can be hard to delineate what's factual, what's misinformation, and what's disinformation. So to do that automatically, which you'd have to do to get a large scale quantification, I think is a really tough task.
Chad messaged in, it would be interesting to see a heat map of the USA showing disinformation. Yeah.
We're trying some of that with COVID. We have some, not geolocated, but we have who talks to different governors, and we're going to play with that. But it would be interesting, but especially with the election data as well. We do think that conversations in swing states were probably more likely to be laced with disinformation, but that may not be because the people in the swing states were talking about it. It's probably more because the rest of the country was talking about those more.
Yeah, I would actually say that, like, you now working on COVID, I mean, is it easy to take what you learned and just shift it over to a different topic, or is there a lot of relearning and redoing when you have to do that?
I would say the methods that we're using to unpack narratives in the networking tools, the visualization tools, transfer from context to context. And some of the same accounts are active in both. And some of the COVID misinformation influencers were at the Capitol building on January 6th and were arrested. So they do converge. And yet it is really important, you know, when we think about the 100 researchers that we had in that project, and we now have a much smaller team for the vaccine related misinformation, there's a lot of training that has to happen to understand the context so people can begin to recognize the difference between information, misinformation, and disinformation. And so, and it's contextual, it's related to specific narratives that are spreading. So, so some things transfer really easily and some don't.
Okay. Aria, somebody asked early on about your images, because you used 3 million images to do your experiment. Where did those come from?
So basically, the city has an agreement with a third-party company every 6 months. It is the name of the company is, I think, is Wrapup, and they are a company, I think, the city of Pittsburgh, and they are running through cities, collect a lot of images. So they send all of these images to the city. City do the de-anonymization of this data, and they send us the low resolution data to us.
Do you think you needed all 3 million images? Because I think that go ahead.
Actually, we are not using all of these 3 million images because there are a lot of computation, and we don't really need all of these images to identify cracks and potholes. There are a lot of repetition in all of these images, and they are not necessary information, unnecessary information.
How many do you think you actually need? Because I think that's one things that comes out of this experiment is you could actually advise a city on how to plan this, you know, how to plan to do this right.
This is a very good question. I think this image is collected for many different purposes, and we are using it for quantifying the condition of each road. But there are other people in the city who are using these images for various purposes. Yeah. So we are not the only user of these images. But for us, I think 1% of these images are sufficient to quantify the condition of these roads. And we are not using more than 1% of these images.
I think Chad is wanting to ask you a question. James, will you unmute him to allow him to ask?
Go ahead, Chad.
Oh, hello. Hey, everybody. Arya and Kate, those are fantastic talks. Thank you so much. Arya, a quick question. When Angela had mentioned the image gathering, something came to my mind. I've personally been working on sort of a side project where I've been actually incorporating drone technology and some AI algorithms I've been developing on my own. And where my goal is to use drones, process those images, use AI to look at those images and see if there's faults in structures, for example. Have you guys thought about potentially doing that for any of your research? I mean, it could give you, a really good hands-on control of what streets, bridges, things like that could really use immediate attention, right? Like, for example, taking a drone, flying it down a particular street in Detroit versus like a second street and prioritizing which street would need work first based off of like a grading of those images being brought in via the drone.
For our application, I think this is a very interesting question, and it is a very great viewpoint. But I think for our application, in terms of like quantifying the condition of the road, if you are thinking about like images coming from the drones, they are very low resolution, and it is very hard to identify cracks and potholes. But I think drones can be very useful in quantifying the traffic volume data, because we are using estimates that are not very great, they are very outdated, and it is very expensive to collect this traffic volume data. I think drone images can be very useful to quantify the traffic volume and get updated on this information and keep continuing like updating this information as the dynamics of the city is changing.
Okay, awesome. No, thank you very much.
Yeah, thank you for the question.
Yeah, I want to remind you guys, kind of the goal here is to encourage collaboration. So you guys should, if you see a place where there's synergy here, I think Kate and Arya would be want to hear from you. And also, I think someone asked earlier about slides, and if you reach out, they'd be happy to share. And I also wanted to point out, because somebody else also pointed out, Arya has a Python package that he will be making available in 2021, but it sounded like on your slides, you would be willing to share if people emailed it to you.
Still, I need to clean up the package and put it in public domain, but I would be happy to share the code and the algorithms with anyone who is interested to work with us.
Yeah. The best way to make sure you get, you get some feedback, then it forces you to get it out. It stood out when I was watching because you focused on, urban analytics, but it really seemed like there'd be a lot of like applications like in the biomedical field where, it's like we have to be extremely careful about demographics and, biases and how we treat people. Are you collaborating with anybody there?
Actually, my background is in astronomy, and I'm using a lot of these applications for astronomy, especially when we are talking about like trustworthiness of predictive models. We want to make sure that these models are a good fit to the data. And it is exactly the type of question that we are answering here. Here we are framing it in a different language, and we are trying to apply it to a different domain and extract different knowledge. But I'm using exactly the same algorithm to quantify the predictive model that we are applying to the astronomical domain, and how we can quantify the machine learning algorithms and make them more useful for the sciences that we are doing in astronomy. But this is a very good question. And all of these algorithms and techniques can be broadly applied across different domains.
Yeah. Well, I can see it's 3 o'clock, or it's 3 o'clock in my time zone. I think we're all on different time zones. I will, again, thank you guys so much for speaking. Really interesting talks. I look forward to hearing more from you guys. And, I hope to see some collaborations come out of this.
Yeah, thank you so much.
Yeah, thank you. Nice to meet you, Arya.
Nice to meet you.